Hello Science 9, welcome to your second lesson on space, which is primarily about telescopes and then also getting into satellites. So, how do we see objects far away? Well, we use a telescope. Telescopes can magnify objects that are far away, and telescopes have an objective lens typically, and then an ocular lens that we look through. The telescope was first invented by Hans Lippershey and improved by Galileo. Not important for you to know about Hans. Galileo is fairly important because of the fact that he took a look at Jupiter and its 4 moons. And from here, you could see that those moons were rotating around Jupiter, which showed kind of this idea that maybe that geocentric point of view is wrong because you actually saw the moons rotating around Jupiter instead of rotating around Earth. So this supported, of course, the heliocentric model, showing that things can rotate around stuff besides the Earth. So there's 2 main types of telescopes we're going to talk about, and then kind of a third that's a combination of the 2. We have refracting telescopes, and they use an objective lens to gather light. So you know all about refraction from the optics unit in grade 8, hopefully, and the fact that light bends as it goes through surfaces of different optical density. So we'll take a look at some diagrams, but basically light gets bent from a larger opening to go to a smaller opening, and that's how we get the magnification. Reflecting telescopes instead use a mirror. So we call it an objective mirror to gather the light. It still typically goes through a lens, but then goes through an objective mirror. And then that objective mirror ends up reflecting the light at an angle, again, to bring a larger kind of area of light to a smaller area so that we magnify the object. If you have a reflecting telescope and a refracting telescope of the same size, the refracting telescope will provide clearer images, so the ones with the glass inside of it, but reflecting telescopes can be made much, much larger, which means that we have more ability to magnify with the reflecting telescope, which uses a mirror. So really important to understand that refracting is all about lenses, while reflecting is all about mirrors. Modern telescopes actually use a combination of lenses and mirrors together, and they're called either compound or, I might say this wrong, cadadioptric. I'm saying that wrong. Cadadioptric telescopes. All right, maybe I'll put in a video about how to pronounce it afterwards. I've always just called them compound telescopes in the past. So here's kind of a image showing a refracting telescope. So it's going through a lens and the light is bending as a result. So you can see light that is quite large, and then it's going smaller and smaller and smaller so that we can see a large area in a smaller area with our eye here as it goes through the ocular lens. And that's how it magnifies, as it goes from big to small for the light. So therefore we can actually see things much closer up than we would otherwise. Here is another one showing a refracting telescope, but we're going to pass through that. This is the image I wanted to look at. Here we have our refracting telescope, again going through the lenses that are bending light. In a reflecting telescope instead, we have the light going in. It goes off of the primary mirror, which causes things to reflect at an angle and go smaller. And then it goes through a secondary mirror and then finally to the eyepiece. And then if we have a really fancy mix between the two, this is where we actually have, again, mirror systems going on, but then we have also an ocular lens that we're looking through and a corrector plate as well. So we have a combination of both lenses and mirrors to get a fantastic image out of it. And I'm not going to try to say that again. We'll just say compound telescope. And I think that is the term that we use in testing. Well, I know it's the term we use in testing, is compound telescope instead. All right, so let's talk about resolving power, which is one of the things we talk about with telescope. It's the fine detail that the telescope can produce. So when you have something that has a high resolving power, you're going to see more of the details, which is different from magnifying, right? When you magnify, you might see a large image, you might see something really up close, but it might have a bad resolution. So a best telescope will have both high magnification and it will have high resolving power, which allows us then to see more detail. So to build a more powerful telescope, you need to increase the resolving power, which is done by either increasing the diameter of the objective lens, and there we're talking about a refracting telescope, And then also increasing the distance between the objective and the ocular lens, again, talking about a refracting telescope. That could also be the objective and the reflecting mirror or secondary mirror, right, when we're looking at a reflecting telescope. So essentially, with telescopes, bigger is better. It's going to give you a better resolving power, and you'll also be able to get higher magnification as well. So larger telescopes are something that you learned a little bit about in that podcast when we looked at the mountain in Hawaii where they have tons of telescopes, and because of the high altitude, there's a huge advantage there when it comes to not having as much atmosphere between space and celestial bodies and the telescopes themselves. In 1773, William Herschel built one of the largest refracting telescopes to date, and actually used that to discover Uranus. Some people say that Uranus to avoid the jokes, but I think officially we're supposed to say Uranus. Anyways, so kind of neat that a planet could be discovered using telescopes, and this really, really large one from William Herschel. So telescopes on Earth are tricky. They have a hard time sometimes getting clear views, and a lot of that has to do with the atmosphere and cloud cover and stuff. Right, so cloud cover, obviously a massive problem. As we get to higher altitudes, it's not as much of a problem, which is why that mountain on Hawaii is such a good place for it, because it's above the clouds most of the time. But there's still atmosphere between the celestial bodies that we're trying to study and the actual telescope, and that causes issues. It causes like glimmering and shifting and so on that distorts our view. So currently scientists use computers to enhance the quality of images from ground-based telescopes to remove the effects of the atmosphere or the twinkling effect. You've probably seen this when you look even up at normal stars, where you see that the star is kind of twinkling, and that is due to movement of atmosphere. It's actually due to refraction. So as light from the star is moving through different densities of air, it bends around and moves, and that causes the twinkling that we see, the twinkling of the star. And it's because of these pockets of cold and warm air that are always shifting around and moving, causing the light to refract in different ways. The star itself isn't actually moving or twinkling. It just has to do with the atmosphere. So we have adaptive optics, and I feel like the slide is a little bit out of order, but it's not going to be a huge deal. Adaptive optics get rid of this twinkling. They use computers to actually adapt the mirrors and the images that come from the telescope in order to adjust for Earth's atmosphere, which does a really good job of creating clearer images. So those mirrors, when we take a look at this kind of image of showing a bunch of mirrors that are mounted, will actually move around based on the movement of the atmosphere, based on the refracting that's occurring, to adjust for it so it doesn't show up in the images. So as optical telescopes use visible light waves to produce images that we see, visible light is only part of the electromagnetic spectrum. There's more out there, right? Again, this ties into hopefully what you learned about in grade 8 about different things in the electromagnetic spectrum when you learned about light. So visible light is just a very, very tiny part of that spectrum. And we also have, of course, things like X-rays and gamma rays and ultraviolet radiation, infrared radiation, and radio waves and so on. So we can use these different waves to actually learn things about space as well. And one of the main types of telescopes that are used are radio telescopes to tell stuff about space. So here is the electromagnetic spectrum, right? And we're going from really short wavelengths when we get to gamma rays to longer and longer and longer wavelengths when we get to things like radio waves. Visible light is right here. You can see a very tiny part of the electromagnetic spectrum. So what we're going to talk about is actually telescopes that use radio waves instead. And in 1932, Carl Jansky built the first radio telescope. It looked like an antenna and he found that the planetary radio emissions were interfering with communication signals on Earth. So to create an image from a radio telescope, computers receive the signal from the telescope and assign a color. And the color is based on how intense the signal is at that point. So blue is lower intensity, and then as we get higher and higher in intensity, we get greens, yellows, reds, and then finally whites for the highest intensity. So when we take a look at this diagram, blue is low intensity, and then we have red that's actually quite high intensity. Very similar to like an infrared image, right? When you look at an infrared camera, same kind of deal, but this is instead tracking radio waves, and this tells us a ton about space and celestial bodies. Radio telescopes have a lot of advantages over optical telescopes, such as radio waves can go through dust clouds, right, which light cannot do. Radio waves are not affected at all by the weather. Radio waves can be detected during night and day, and radio waves are not distorted by clouds, by pollution, or the atmosphere. So super handy. We can view more at all times. Stronger radio waves produce an image that is more red, and weaker radio waves produce images that are more blue. We already talked about this. The best images or best data that we can get is by combining radio wave data, right, radio telescope data, with optical data. So what we would get from very large telescopes that can see visible light. And by combining the two together, we can get a fuller picture of what's going on. And that's how we can learn the most about stuff in space. Bigger waves mean bigger telescopes. So this is actually, I know it just looks like a satellite dish, but that is a radio telescope. And bigger means that I can catch bigger waves. And what I mean by bigger waves is larger wavelengths. So radio waves are longer by far than light waves. They're like kilometers long. So we need a larger telescope to get a better resolving power. And they're not necessarily kilometers long. We have ones that are meters long as well. But when you compare it to visible light, that is in nanometers. So that's times 10 to the negative 9 meters. So they're incredibly tiny in comparison to radio waves. So larger telescopes, radio telescopes, again, means that we have higher resolution images. As we have smaller telescopes, we have lower resolution. But there's tricks around this, how we can get even higher resolution with combining information from radio telescopes. And that's called interferometry. So in interferometry, we use radio telescopes that are a distance apart to get an image equal to having a large radio telescope the size between the two. So if we have two radio telescopes that are 50 meters apart, and then we're monitoring both of those, then we can combine those signals, and it's like we have instead a telescope that is 50 meters in diameter. So by combining two telescopes together and the data we're getting from it, it's like we're actually getting information from a telescope that is the size of the distance between those two telescopes. And that's called, again, interferometry. Really neat. So kind of the next step for this, so we can get even larger, is we can take a radio telescope that's in space and then also the data from one that's on Earth. And then it's like we have this massive radio telescope that's kilometers and kilometers wide. The largest interferometry system is the Very Large Array Telescope system in New Mexico. And this is a picture of that. You can see that it's in kind of this triangle pattern type thing, right? Where we have all these telescopes that can then be combined to make it so that we have a telescope that's actually like this large right here, very, very large, the distance between. And that can give us great, great data. To get an even greater distance, we just talked about this, we can use a technique called very long baseline interferometry. And that's where a satellite in space and radio telescopes on Earth are combined to give a sharper image. And it's like then that we have a satellite dish that is this large by combining this radio telescope signal with the signal that we have from a radio telescope on Earth. So here's a neat question from an old PAT. This is a Hubble telescope diagram, and it's asking, first of all, what kind of technology it uses. So the Hubble Space Telescope uses blank to blank the light into the focal point. And you can see the focal point is actually measured right there. So is this showing lenses or mirrors? And the answer is, this is a mirror, right? It's reflecting off. This is a mirror. It's reflecting off. You can tell because it's not going through these things, right? If we have refracting lenses, it's going through those lenses. This instead is reflecting off of it. So I have mirrors and reflect. The answer would be C. So last thing we're going to talk about today is satellites, and specifically artificial satellites. Just a little bit of history around this. Artificial satellites are man-made devices that can be used for communications, observations, navigation, and mapping. Sputnik was the first artificial satellite that was launched into space, right? It was launched by like Soviet Russia, USSR, back in the day. And then Alouette 1 was the first Canadian artificial satellite that was launched into space. So that's a bit of a Canada connection. I'm not sure what year that was. The Hubble Space Telescope that you just saw in that question is a very important satellite to understand because of the amazing images it gives us. The Hubble Space Telescope is a telescope that is outside of Earth's atmosphere, so as a result, it can get very, very clear images. As you learn in that PAT questions, it's a reflecting telescope, and it's always moving around, okay, the Earth, which allows us to take images of different things. We should take a look at some images from the Hubble Space Telescope. It's really quite neat. But big advantage is it's outside of the Earth's atmosphere, so we don't get that twinkling effect, that distortion from the atmosphere. We don't have to worry about clouds, so it gets much clearer images than we can get on Earth. GPS is something that we all know about. Now all of our phones are kind of connected to GPS, so we don't need these GPS units as shown in the picture anymore. But GPS system is based on signals from 24 satellites that are moving around the Earth all over, all the time. And they're sending out time signatures. So they're just sending out like pings, right? Saying, here I am, and here's my location. And by using those signals from GPS satellites, we can figure out where our position is on Earth. So we can do what's called triangulating as long as we are in range of 3 signals out of the 24 satellites. So 3 satellites can be reached out of the 24 that we can actually get the signal from them. Then we can figure out location by triangulating it. So GPS was originally developed for missile tracking for war purposes, but over time, of course, it's come into consumer products. These satellites are not geosynchronous. This is a term we need to talk about. Geosynchronous means that it is above the same point on Earth all the time. Instead, GPS satellites move around the Earth every 12 hours, so they're just zooming around very close to Earth compared to other satellites or like geosynchronous satellites in order to send those signals so people can triangulate their position. Geosynchronous satellites are communication satellites typically. So when we have communication satellites, like for example, for satellite television and stuff, that's always pointed in the same position, right? Those satellite dishes don't move. And that's because they're pointing to a specific communication satellite. Or if they do move, they're moving to pick up a different satellite. But normally communication satellites are always geosynchronous. In other words, they're always above the same place on Earth. So this is a diagram trying to show GPS, right? So if this person is backpacking and taking a look at their GPS unit, they're receiving signals from 3 different GPS satellites that are moving around. And based on those time signatures, it can figure out where the person is and triangulate it and then show them that information. Remote sensing satellites are artificial satellites that take scientific measurements. So we heavily rely on remote sensing satellites for a lot of our scientific data. They can show many things like how healthy versus unhealthy vegetation on Earth is by looking at changes in colors that are occurring. They can map clear-cut and burned forests to show the rate of their degradation. They can even do imaging and stuff using sensors to figure out water pollution. They can track erosion throughout the Earth and observing land use in cities and tracking weather. So satellites are incredibly useful in order to actually figure out stuff around the health of our Earth and what's happening and to track different things that are occurring. So they are neat. Space probes are made to conduct science experiments. They do not have people on them, so they're unmanned spacecraft. And space probes have helped scientists get information about our solar system. Most probes are not designed to return to Earth. They just go out there and then they're gone, but they send signals back to Earth so that, data that's collected can be analyzed. Some probes have landed on other planets, like for example, Mars. We'll probably watch a video or two around that. And others have flown past the planets and taken pictures of them for scientists, which is also kind of neat. And when those probes get further and further out into space, it takes a long time for that signal to make it back to Earth. So that's space probes. Neat stuff. That's it. That's all we're doing for today. So you learned a little bit about different types of telescopes. You learned about radio telescopes and interferometry. And then finally, you learned a little bit about satellites and space probes. All right. Have a good rest of your day.